Hello everyone. Today we're talking about our case study DMA analysis and pressure-based leakage reduction. This course introduces a real-world case study to demonstrate how the concepts covered in previous courses are applied in practice. While theoretical knowledge and analytical methods are essential, real implementation involves additional technical, operational, and organizational considerations that can only be understood through applied examples. The Ecological project is positioned as the final step in the learning progression of this curriculum. It builds directly on the fundamentals of urban water networks and pressure management covered in Course 421, as well as the data-driven leakage detection and intervention planning methods introduced in Course 422. Together, these courses form a complete workflow from theory to application. The main learning objective of this course is to understand how DMA-based analysis and pressure-focused leakage reduction strategies are implemented in a real project. Learners will explore how GIS-based decision support systems translate analytical results into operational actions and how these actions contribute to reducing water losses in urban networks. Urban water loss is a complex problem that includes both physical and apparent losses. Physical losses occur due to leaks, bursts, and overflows in the distribution network, while apparent losses are related to metering inaccuracies, data handling errors, or unauthorized consumption. Both types contribute to non-revenue water and reduce system efficiency. Cities face several challenges that intensify water loss problems. Aging infrastructure increases the likelihood of failures, while high variability in demand creates fluctuating pressure conditions that stress network components. In many cases, limited monitoring coverage makes it difficult to detect losses early and accurately. Because of these challenges, generic or purely theoretical solutions are often insufficient. Water loss behavior is highly dependent on local network characteristics, operational practices, and data availability. Case-based solutions, such as the Ecological project, provide valuable insight into how tailored approaches can address real-world conditions more effectively. The Ecological project was developed in response to persistent water loss challenges in urban distribution networks. Many municipalities face high levels of non-revenue water, driven primarily by physical losses that cannot be effectively managed using traditional methods. Conventional approaches to water loss management often rely on fragmented data sources and manual analysis. Operational data, asset information, and consumption records are typically stored in separate systems, making it difficult to obtain a comprehensive view of network behavior. As a result, loss management tends to be reactive rather than proactive. Ecological was designed to address these limitations by providing an integrated, GIS-centered decision support system. Its main objectives are to enable DMA-based leakage analysis, support pressure-focused loss reduction strategies, and translate analytical insights into actionable operational decisions. This integrated approach allows utilities to manage water losses more systematically and effectively. The Ecological project is designed as a comprehensive solution for managing physical water losses in urban distribution networks. Its scope focuses on combining DMA-based analysis with pressure optimization strategies to reduce leakage and improve overall network performance. The project progressed through a structured research and development phase, followed by pilot implementations in real urban networks. These pilots allowed the system to be tested under real operational conditions and refined based on practical feedback. Over time, Ecological evolved from a prototype into an operational decision support tool. Key stakeholders involved in the project include municipal water utilities, technical and operational teams responsible for network management, and decision-makers who use analytical outputs to guide investments and interventions. This multi-stakeholder structure reflects the collaborative nature required for effective water loss management. The Ecological system is built on an integrated and modular architecture designed to support operational decision-making in urban water loss management. The architecture is scalable, allowing it to be adapted to networks of different sizes and levels of data availability. Ecological operates as a data-driven analytical monitoring platform. It complements hydraulic modeling tools but does not replace them. Its primary function is performance evaluation and decision support. At its core, the system consists of three main components: The first is a GIS-based network model that represents the physical structure of the water distribution system, including pipes, DMAs, and assets. The second component is the data analytics and modeling layer, where flow, pressure, and consumption data are processed and analyzed to identify losses and generate scenarios. The third component is the reporting and visualization layer, which presents analytical results in an accessible and actionable format. Data flows into the system from multiple sources and is processed through analytical workflows before being transformed into decision support outputs. This structured data flow ensures that complex analytical results can be translated into clear insights for operational teams and decision makers. A UKIP relies on the integration of multiple data sources to provide a comprehensive view of water network behavior. GIS-based network data form the spatial backbone of the system. This includes pipe geometry, network connectivity, valves, meters, DMA boundaries, and detailed asset attributes such as material, diameter, and installation age. SCADA systems provide flow and pressure measurements that describe how water moves through the network over time. Both real-time and historical data are used to analyze operational conditions, identify anomalies, and support pressure-based analysis at inlet and zone levels. Consumption and billing data add a demand-side perspective. Customer usage records are used to estimate expected consumption within each DMA and to support water balance calculations. Integrating these datasets allows a UKIP to compare supplied water with expected demand and identify discrepancies that may indicate physical losses. Geographic information systems play a central role in the UKIP project by providing a spatial representation of the water distribution network. Pipes, DMAs, valves, meters, and other assets are visualized on a map, allowing users to understand how the network is structured and how different elements are connected. GIS also enables operational data to be linked directly to specific locations within the network. Flow, pressure, and consumption measurements gain meaning when they are associated with particular pipes, zones, or DMAs. This spatial linkage allows analysts to interpret anomalies more accurately and identify where losses are most likely occurring. In addition, GIS supports decision-making through visualization tools such as thematic maps and dashboards. By presenting analytical results in a spatial and visual format, a UKIP helps both operational teams and decision-makers understand complex information quickly and make informed intervention decisions. In real water distribution networks, a district metered area is a hydraulically isolated section where water inflow can be accurately measured and monitored. By defining clear boundaries using valves and control elements, utilities can analyze water behavior within a limited and well-defined area. In this course, DMA is treated as an existing operational monitoring unit rather than a design concept. The physical segmentation and hydraulic isolation processes are outside the scope of this training. The focus is on performance evaluation within already established DMA zones. DMA-based analysis is essential because it allows losses to be detected at a localized scale. Instead of analyzing the entire network as a single system, DMAs make it possible to identify where losses are occurring and to compare performance between different zones. This localized approach significantly improves monitoring accuracy and supports targeted interventions. In the UKIP project, the DMA concept is applied in a practical and flexible manner. DMA boundaries are defined based on existing infrastructure conditions and available measurement points. This adaptability allows a UKIP to be implemented even in networks where ideal DMA configurations are not fully achievable, making the approach suitable for real-world urban systems. The physical boundary design of DMAs is not addressed in this course. Instead, we evaluate how existing DMA configurations influence data availability, pressure monitoring, and analytical performance assessment. Designing and configuring a DMA is a critical step in effective water loss management. The first task is defining clear DMA boundaries by identifying points where the network can be hydraulically isolated. Valves and other control elements are used to create these boundaries and ensure that water entering the DMA can be accurately measured. Selecting appropriate inlet and measurement points is equally important. Flow meters are typically installed at DMA inlets to measure incoming water, while pressure sensors may be placed at strategic locations within the DMA. Reliable measurement is essential for accurate analysis and water balance calculations. In real networks, DMA design is often influenced by operational constraints. Existing infrastructure limitations, incomplete valve isolation, and data gaps can affect ideal DMA configurations. The Ecological approach acknowledges these challenges and supports partial isolation and adaptive configurations, enabling practical implementation under real-world conditions. DMA performance indicators are used to evaluate how effectively each district operates and to identify areas with high water losses. One of the core analytical elements is the water balance, which compares the total volume of water entering a DMA with authorized consumption and estimated losses. Key performance metrics derived from the water balance include physical loss rates and non-revenue water indicators. These metrics provide a quantitative basis for understanding the severity of losses within each DMA and for tracking changes over time. Comparative analysis across multiple DMAs is a powerful feature of the Ecological approach. By benchmarking DMAs against each other, utilities can identify zones with disproportionately high losses and prioritize them for further investigation or intervention. This comparison supports data-driven and transparent decision-making. Physical losses represent water that escapes from the distribution network due to leaks, bursts, and overflows. These losses are directly related to the physical condition of the infrastructure and are strongly influenced by operating pressure levels within the network. In the Ecological project, physical loss modeling is carried out at the DMA level. The modeling logic is based on comparing measured inflow volumes with expected consumption values derived from billing and demand data. The difference between these values provides an estimate of physical losses within each DMA. Network-specific characteristics play an important role in interpreting modeling results. Factors such as pipe material, installation age, total pipe length, and connection density influence leakage behavior. By incorporating these characteristics into the analysis, Ecological provides a more realistic and context-aware estimation of physical losses. Pressure is one of the most influential factors affecting physical water losses in distribution networks. As pressure increases, the rate of water escaping through existing leaks also increases. In addition, sustained high pressure accelerates the deterioration of pipes, joints, and fittings, leading to new leaks and failures over time. In the Ecological project, pressure leakage relationships are analyzed at the DMA level. Pressure profiles are generated using average, peak, and nighttime pressure values to understand how pressure behaves under different demand conditions. Nighttime pressure is particularly important, as high pressure during low demand periods often correlates with increased leakage. These observations have direct operational implications. Unlike some other loss factors, pressure is a controllable variable. By understanding how pressure influences leakage within each DMA, utilities can develop targeted pressure optimization strategies to reduce physical losses while maintaining acceptable service levels. Pressure-based leakage reduction is a central strategy in the Ecological project because pressure has a direct and measurable impact on physical losses. Reducing excessive pressure often produces faster and more cost-effective results compared to large-scale infrastructure renewal projects. In Ecological, pressure reduction strategies are evaluated at the DMA level. Each DMA is analyzed individually to assess current pressure conditions and to identify how much pressure can be safely reduced without compromising service quality. This localized approach allows for targeted and efficient interventions. Operationally, the strategy is based on maintaining pressure at the minimum level required to ensure reliable service. Special attention is given to avoiding overpressure during low demand periods, such as at night, when leakage risk is highest. This balanced approach helps reduce losses while preserving customer satisfaction. Pressure optimization scenarios are developed in Ecological to evaluate how different pressure adjustment options may affect leakage and network performance. The process begins by analyzing baseline pressure conditions, including existing average and peak pressure levels across each DMA. This analysis helps identify zones where pressure exceeds operational requirements. Based on baseline conditions, multiple pressure reduction scenarios are simulated. These scenarios represent different levels of pressure adjustment and allow decision makers to explore various optimization options. Each scenario is evaluated to understand its potential impact on leakage and service quality. Pressure optimization scenarios in a UKIP are evaluated analytically using measured data trends. The system does not perform full hydraulic network redesign but assesses operational adjustment potential within existing configurations. Expected outcomes of pressure optimization scenarios include a reduction in physical water losses and improved pressure stability across the network. By comparing scenarios, utilities can select pressure settings that achieve the best balance between loss reduction and reliable service delivery. A UKIP generates a range of decision support outputs designed to help utilities interpret analytical results and take informed action. Dashboards and thematic maps present key indicators related to losses and pressure at the DMA level, allowing users to visually compare performance across different zones. Scenario evaluation outputs play a critical role in decision-making. By comparing baseline conditions with optimized pressure scenarios, a UKIP quantifies the expected impact of pressure adjustments on physical losses. These comparisons help decision-makers understand trade-offs and select the most effective intervention options. The outputs of a UKIP are designed to guide operational decisions. The system provides comparative performance analysis rather than hydraulic simulation-based design outputs. Overall, the system is designed to translate complex analytical results into clear and actionable insights. By supporting prioritization and scenario-based evaluation, a UKIP enables utilities to make evidence-based operational and strategic decisions. Intervention planning is the stage where analytical insights are transformed into concrete operational actions. In the UKIP project, this involves translating model outputs and scenario results into clear tasks that can be implemented by field teams. DMAs are prioritized based on their potential for loss reduction, as well as practical considerations such as cost, accessibility, and operational feasibility. This prioritization ensures that limited resources are directed toward interventions with the greatest expected impact. Different types of interventions may be considered depending on the analysis results. These include pressure control adjustments, targeted infrastructure repairs or renewals, and enhanced monitoring activities. By combining analytical evidence with operational planning, a UKIP supports efficient and effective leakage reduction strategies. Operational implementation focuses on integrating analytical insights into daily field operations. In the UKIP project, this requires close coordination between analytical teams and field crews to ensure that intervention tasks are clearly defined, properly scheduled, and aligned with operational priorities. Monitoring plays a critical role both before and after interventions. Baseline conditions are established prior to any action, allowing changes in flow, pressure, and loss indicators to be measured accurately after implementation. This comparison provides objective evidence of intervention effectiveness. Field results are then fed back into the UKIP system. By updating analytical models with real-world outcomes, the system continuously improves its accuracy and reliability. This feedback loop supports adaptive management and long-term performance improvement. The impact assessment stage evaluates the results achieved through DMA-based analysis and pressure optimization in the UKIP project. From a technical perspective, interventions lead to measurable reductions in physical water losses and improved pressure stability within targeted DMAs. Operational and economic benefits are also significant. Lower levels of non-revenue water translate into cost savings, while reduced leakage and stabilized pressure decrease the frequency of repairs and emergency maintenance. These improvements help utilities allocate resources more efficiently. Beyond immediate operational gains, the project has important sustainability implications. By reducing water losses and optimizing pressure, a UKIP supports more efficient use of limited water resources and contributes to the long-term resilience of urban water networks. The UKIP case study provides several important technical lessons. One key insight is that the quality of DMA design and configuration has a direct impact on the accuracy of analytical results. Poorly defined DMAs limit the effectiveness of leakage detection and pressure optimization. Data-related challenges are another critical learning area. Reliable results depend on the completeness and quality of integrated datasets. The successful integration of GIS, SCADA, and billing data is essential for building an accurate and actionable decision support system. Finally, the case highlights the importance of organizational and operational factors. Strong coordination between analytical teams and field operations, combined with iterative implementation and continuous monitoring, are key success factors in achieving sustainable water loss reduction. This course demonstrated how DMA-based analysis and pressure optimization strategies can be applied in a real-world project through the Ecological case study. By integrating spatial data, operational measurements, and analytical methods, Ecological provides a practical framework for reducing physical water losses. The approach presented in this case study is not limited to a single city or network. The principles of DMA-based analysis, pressure optimization, and GIS-supported decision-making can be adapted to different urban contexts and varying levels of data availability. Together, courses 421, 422, and 423 form a complete learning pathway. Starting from network fundamentals, progressing through data-driven analytics, and culminating in real-world implementation, this curriculum equips learners with both theoretical understanding and practical skills for modern urban water loss management.